Welcome to The Explainer. Today we're talking about a seriously cool AI that could completely change how we keep our most important structures safe. You know, our bridges, buildings, all of it. It's called MIONet, and it's basically giving our physical world a digital nervous system. So, let's start with a big question. Imagine a heavy truck speeding across a bridge. Can that bridge tell us, right at that very second, how it's handling the stress? Can it give us an instant health report? For the longest time, the answer has been, well, not really. And that tiny delay, it's a massive problem.
And this slide shows you exactly why. A real-world event is over in milliseconds. But our best tools for understanding what just happened are computer simulations. They can take hours, sometimes even days, to give us an answer. This huge time difference is the simulation gap, and it's what engineers have been desperately trying to solve for years.
Now that gap isn't just some technical hiccup. It's a legitimate billion-dollar problem that has a direct impact on safety. If we want to monitor our infrastructure in real time, we have to close that gap.
You see, the gold standard for this stuff is called the finite element method, or FEM. It is incredibly powerful. It works by digitally breaking a bridge down into thousands of tiny little pieces to calculate all the forces. But doing all that math takes a ton of computing power and, here's the key, a ton of time. It's fantastic for designing a bridge in the first place, but way too slow to monitor one live.
So, if the old tools can't keep up, what's the answer? Well, this is where the hero of our story comes in, a brand new type of AI designed to be an instant predictor.
Meet MIONet. It stands for Multiple Input Operator Network. And what it does, at its core, is learn to predict how a structure is going to react under stress, but it does it almost instantly. It's built to understand the continuous flow of forces across the entire structure and over time, letting it completely leapfrog those slow, traditional simulations.
So what's its secret? Well, it builds on an older AI framework called MIONet, but with a game-changing upgrade. It doesn't process information one step at a time, which is what slows other models down. Instead, MIONet is designed to see the whole picture, the entire event, across the whole bridge for the whole duration, all at once. That makes it the perfect tool for creating a digital twin, which is basically a live virtual copy of a real-world bridge.
Okay, so how does it actually pull this off? The architecture behind it is pretty complex, but we can actually understand it with a pretty simple analogy.
Just think of MIONet as this master chef who doesn't even need a recipe. They can just glance at the ingredients, they know their kitchen inside and out, and they understand the final dish so perfectly that they can create it in one single fluid motion. MIONet operates in a really similar way, using 3 specialized brain centers or networks. So first up, you have the branch network. This is like the chef checking out the ingredients. It looks at all the inputs, the truck's speed, its weight, the forces it's creating. Then there's the spatial trunk network. This is the chef's total knowledge of their kitchen. It has a perfect map of the entire bridge, knowing where every single point is. And finally, the temporal trunk network is all about the timing. It pinpoints the exact moment in time that we need a prediction for.
And here is where the magic happens. MIONet uses this really clever mathematical operation to instantly combine the information from all 3 networks. It fuses the what, that's the load, the where, the bridge's structure, and the when, the exact time, to produce a single, incredibly accurate prediction of how the bridge is responding.
An AI that can predict a bridge's future is, well, it's amazing. But how do we know it's actually right? Well, that brings us to MIONet's secret sauce, how it learns. See, MIONet isn't just memorizing a bunch of old simulations. It's actually being taught the fundamental laws of physics. It learns the core equations that govern how forces and mass have to behave in the real world. It's a hybrid approach, part data, part physics textbook. And this training method is super flexible. It gives researchers some powerful choices. If all you care about is raw speed, you can train the model on data alone and get pretty good results fast. But if you need the absolute highest accuracy, you can bake those laws of physics right into the training. It takes a bit longer, but it pushes the model's accuracy to the max. You can find the perfect balance for any job.
And why is that so important? Because training it with both data and physics means the AI's predictions aren't just statistically probable, they are physically plausible. It keeps the model grounded in reality, which is, absolutely essential when you're talking about the safety of a billion-dollar bridge. All right, let's get to the results. What does all this fancy AI architecture and training actually get you in the real world? Well, the impact is, and I'm not exaggerating, a revolution. 100 times faster.
In head-to-head tests, MIONet delivered its predictions over 100 times faster than the traditional gold standard simulations. Just let that number sink in for a second.
And here's the real kicker. All that incredible speed doesn't mean you sacrifice quality. The model still achieves over 95% accuracy when compared to those super slow, super detailed simulations. So you get the speed of an AI prediction with the accuracy of a deep simulation. It's truly the best of both worlds. To put it another way, a calculation that used to take minutes or maybe even hours can now be done in a fraction of a second. That simulation gap we talked about at the beginning, it's basically gone.
And closing that gap unlocks a future that until now has been pretty much science fiction. We can build true digital twins, live virtual models that perfectly mirror our real infrastructure. We can get instant safety alerts if a structure is in trouble. And, maybe most importantly, we can finally shift from fixing things after they break to a world of proactive maintenance, catching problems before they ever become dangerous.
This really is the beginning of a digital nervous system for the world we've built. It's like we're giving our infrastructure the ability to feel stress and to tell us about it right when it happens.
Which leaves us with one last, really exciting question to think about. If we can now give a bridge a sense of touch, a way to communicate its own health in real time, what other parts of our world could we bring to life next? The possibilities, honestly, are just getting started.